Okay, let us make a start. Sorry about the slight delay, wrestling with the task of restarting this computer. The University of Melbourne must have the slowest computers on the planet, I think. So, lovely to see you here on this bracing spring day, and I hope none of you ended up none of you are soaking wet and sitting there shivering. It's not the nicest day to be out. I thought I might be completely on my lonesome in an empty lecture theatre. Anyway, it's great to see you here. So we're taking up the next chapters of our attention story, and the rubric, the general heading for the first part of today is structural and capacity theories of attention, for reasons which will become progressively apparent with the unfolding of the story. There are some, again, relevant readings. There's a short excerpt from chapter 4 from Goldstein, pages 91 to 104 are relevant. That was probably something happening in the background, which I had tried to queue up, and who knows how that will all work. We will see. The universe will unfold, not necessarily as it should, but certainly as it will. There is another chapter from Donald Norman's old, but as I recommended to you, highly informative book, Memory and Attention, called A Capacity Model of Attention, and also a short chapter from Elizabeth Stiles' more recent book on attention called Divided Attention. In a sense, there is a fair amount. These readings are not covering exactly the same material. There's a fair amount of overlap, but there are some unique features as well. Okay, so in the second half of last lecture, we looked at what we called the early versus late selection debate, which was the dominant theme in attention research in the 1960s, which was really looking at developments from Broadbent's filter theory. So filter theory was really the claim, as you remember, that attention acts as a filter that protects a limited capacity channel from overload. It sits between the senses and all of the information potentially available from the environment, and this limited capacity channel that's responsible for making sense of the world, but the limited capacity channel can only deal with a limited amount of stuff at a time, and so the filter protects it. So the filter acts to decide what's relevant and to let what's relevant through into the limited capacity channel while excluding other stuff. And so all of the argument that then developed from this was about what got through the filter and where the filter was located. And we looked in the latter part of last week at the competing claims and competing evidence of two alternative theoretical views called early versus late selection theory, which disagreed about how far up the sequence of processing operations the filter was located. So if we identify the limited capacity channel, the thing the bit of the system that makes sense of the world with long-term memory, where all of our stored knowledge about the world, including about language, is located, early selection theory says that the filter was before long-term memory, the limited capacity channel, and controlled what got into that system. Late selection theory said it was afterwards, so that the filter, the selective filter that determined what got into consciousness, was actually after long-term memory. And we looked at competing evidence. The evidence for early selection theory were things like Treisman and Geffen's TAP study, where they got people to shadow, but to detect the keyword TAP, where it occurred, whether it occurred on an attended or an unattended channel, and people were poorer on the unattended channel, but they weren't at floor, they weren't at zero, and so they said this was consistent with the kind of attenuation account proposed by Treisman, that the filter turned the volume down on the unattended channel, but it didn't completely block it. We then looked at the competing claims of late selection theory, which says that everything gets into the memory system, everything gets into the semantic system, semantic knowledge gets activated on the unattended channel, and we saw evidence for this kind of semantic activation using indirect methods, various cunning techniques designed to show semantic processing on an unattended channel. So Mackay's ambiguous sentence task, which shows that the meaning of a word on an unattended channel subsequently disambiguated an ambiguous sentence in a recognition test, and the work by people like von Wright and Anderson and Stenman, which showed that a classically conditioned galvanic skin response to words of particular semantic category was still visible, was still measurable when those words were on an unattended channel. Now, that of course wasn't the end of the story. Despite those late selection theory demonstrations being, I think you will agree, striking and compelling, early late selection theory said, well, yeah, that's all true. Our theory doesn't deny that there can be some weak semantic activation on an unattended channel. Your demonstrations, your ambiguous sentence, your conditioned galvanic skin response, shows that there is some semantic processing, some degree of semantic activation on an unattended channel, but it doesn't demonstrate that it occurs to the same extent. Just because you can show it doesn't mean that it's occurring to the same extent. I have a horrible feeling that that's actually we'll ignore that. Might be, I think it's probably related to a YouTube clip that I attempted to queue up, which is pushing myself outside my comfort zone. So we'll see how that all goes. And you know, while this kind of dialogue was going backwards and forwards, there was possibly also a kind of growing sense that despite the fact that these two theories were dressed up in different clothing, the kinds of pictures that were used to represent them, they had more in common than actually told them apart. If you look at, you know, what are the core claims, you know, forget the pictures, and pictures showing where the filter, but you know, what are these two theories claiming? Well, early selection theory says you attenuate the unattended channel, you turn the volume down, and this can lead to weak semantic activation on an unattended channel. It's not as strong as on the attended channel. Late selection theory says that there is brief semantic activation on an unattended channel, which rapidly decays unless the associated material is selected by pertinence. Pertinence grabs it, passes it through the filter to conscious awareness where you can report it. To me, those two claims have a lot in common. Weak semantic activation versus brief semantic activation. There's actually a fair amount of kind of common ground and agreement where they're both saying, well, there is some amount of semantic activation, but ordinarily you're not much aware of it unless under special circumstances. And at the same time that debate was going on, there was growing evidence that there were some phenomena, some experimental results that were not well predicted by either kind of theory. The different kinds of experiments, not necessarily aimed at testing these two theories, predicted findings that were not necessarily well accounted for by either early or late selection theory. All of the tasks, all of the experiments that we've looked up at to date, all of the dichotic listening tasks, lead us to view attention in a particular way. They are filtering tasks. You know, shadowing tasks are filtering tasks preeminently. To do the task, you have to be able to select something to decide, okay, that's relevant, I need to process that, and to exclude the irrelevant stuff. If you can't do that, you can't do the task. And a good example of that was Cherry's binaural listening task that we talked about last week, where he took away the sound localising cues. He asked people to follow one passage of speech where he took away the sound localising cues that are ordinarily present in dichotic listening, and people found that task very difficult to do. Now, this is a parenthetical aside. I don't know if anyone in this audience, possibly not, happened to be listening to the 6 a.m. news last Sunday on ABC Classic FM. I'm probably in a minority of one. And so, you know, since none of you happened to be listening to the 6 a.m. news on Sunday on ABC Classic FM, you will have missed a perfect example of what I was talking about. For some weird reason, the news service during the news service, they actually broadcast two superimposed auditory tracks. Basically two auditory tracks, two voices talking about different stuff at the same time, which of course, coming over a radio was exactly like Cherry's binaural listening task, where you take away the localising cue. And so, I can attest that it was really difficult to follow the news under those circumstances. So here was I sitting up in bed with my coffee at 6 a.m, listening to the news and thinking, selective attention research has come to my bedroom at 6 a.m. on a Sunday morning. It was a unique experience. I'm sorry none of you were able to share it. But moving on, close parentheses. So the point of that, and the facetious aside, is that shadowing tasks lead you to think about attention in a particular way, to think about attentional filtering, the limits of attentional filtering, and conditions under which attentional filtering are more or less, or is more or less efficient. But we can think about attention in another very natural way, which is what happens when we try and divide or distribute our attention. What happens when we try to attend to multiple things at once? So multiple stimuli out there in the world. And that is clearly an important function of attention when we try and attend to multiple things at once. We have a sense that that's probably hard, that there are probably limits to it, and we can study that in a systematic way. And so some of the challenges to the somewhat restricted divided versus early selection view came from studies which asked a different kind of question. Not how well can we shadow, not what are the limits and the efficiency of shadowing and where does selection in shadowing take place, but how well can we divide our attention across multiple channels. Okay, I'm going to talk about an experiment which is complicated. It's actually the most complicated experiment that I'm going to talk about in this sequence of lectures, because the argument involves a comparison of performance in three different conditions. And the inference that the researchers attempted to draw from that is likewise a subtle one. So it requires really a certain amount of effort and possibly some reading to get your head around this argument. It's not necessarily kind of straightforward. So I'm presenting this relatively early in the piece so that even if you hate me now, by the time we get to the end of this sequence of lectures, I hope you'll have forgotten it. Anyway, but it's an old experiment. It's discussed in the reading, chapter 4 of Norman, and I think despite some of its limitations, it remains important and illuminating. So this was an early study at looking at how well and how efficiently people could divide their attention across multiple sources of stimulation, multiple channels. So it was conducted by Neville Moray, he of the cheeky experiment, Your Name on an Unattended Channel fame. And again, he used the technology of the day, the dichotic listening paradigm, presenting two streams of stimuli over stereo headphones to the left and right ear. So his stimuli were a bit simpler than the typical passages of continuous speech that we've been familiar with up until now. And what he presented was just brief, pure tones, little brief beeps, very much like the kind of thing that an audiologist would use if you were having a hearing test. So I've attempted to kind of diagrammatically represent Moray's experiment and the three different experimental conditions, which unfortunately go on to the next slide, in the following way. So these little green rectangles are supposed to indicate brief auditory beeps. So each one of those is a brief beep. And among those brief beeps are occasional beeps of slightly greater volume, slightly greater intensity, which I've drawn as a taller rectangle. And so they were target stimuli which people were supposed to detect. And so I've put a black arrow labelled R, indicating that people's task was to monitor this sequence of beeps, and whenever they heard a target beep, a slightly larger beep, that they made a button press response saying, OK, I detected a target. And so they did that basic target detection task with dichotic presentation under 3 different conditions. Actually, there are a few more, but we'll focus on the relevant 3. So one he called a selective attention condition, where, as you see, people were instructed to say, attend to the stream of beeps on one ear, say the left ear or the right ear, a designated ear, only respond to targets on that ear and ignore anything you hear on the other ear. So that's just like a kind of a dichotic listening shadowing type task. Attend to the contents of one ear, ignore the contents of the other ear. So he called this a selective condition, SEL for short. And when people were able to focus their attention and been instructed to focus their attention entirely on one ear, they detected 67% of these targets. So this was a pretty hard task, right? It's a long way from 100% accuracy. So they're not down around 50%, but so this was a hard task because the difference between the non-target beeps, which they were instructed to ignore, and the target beeps was quite small. Okay, so the selective condition acts as a kind of baseline. He then looked at performance in 2 different divided attention or distributed attention conditions where people were asked to monitor both the left and the right ear for the occurrence of targets. But the way the targets and target presentation was set up was different in the 2 conditions. So he used the jargon of Boolean logic to describe these conditions. So the first, is the one shown here, is called an exclusive OR condition, which in Boolean logic is often denoted by the abbreviation XOR for exclusive OR. An exclusive OR in logic means that it can either be one alternative or the other alternative, but never both alternatives at the same time. What that meant in terms of Moray's experiment was that you could get a target either on the left ear or on the right ear, but never 2 targets at once. But under these circumstances, under the divided attention conditions, the OR conditions, people were required to respond to either. So respond to the target on the left or the target on the right. So what happened? Well, as you can see, there's a cost to dividing your attention compared to when you can focus it just on one ear and exclude the other. So the cost of dividing attention across 2 ears compared to focusing it is that accuracy drops from 67% to 54%. So accuracy takes a hit when you're dividing attention. Okay, that's the first finding. The perhaps interesting bit was that he compared that condition, his exclusive OR condition, to what he called an inclusive OR condition, which in logic is often represented as IOR for inclusive. And what an inclusive OR condition, what inclusive OR as a logical operation means, is that it can either be one alternative or the other alternative, or it can be both alternatives at the same time, which is both alternatives at the same time is represented by as a conjunction, as an AND operation. What that meant in terms of the way Moray did his experiment is in the exclusive OR condition, targets could occur on the left ear, in the case of this alternative, or they could occur on the right ear, or they could appear on both ears at the same time. So what's different to the preceding condition is in the preceding condition, they never occurred on both ears at the same time. Now in this condition, it allows for the possibility that they could occur both at once. And he required that people make distinct responses to, indicating that this was a left target, a right target, or a double target. So on the AND trials, he required them to indicate, I detected 2 targets, not just that I detected one of those 2 targets. Now, with this setup, it's possible to separate the OR trials, the trials in which, although there is a possibility of simultaneous targets, there are never two targets at the same time. So either this first trial, the second trial, and the last trial, so the first and the second both have targets but not simultaneous. Now, under these conditions, on the OR trials, in which the targets were not simultaneous, accuracy was 52% correct, which is not significantly different to 54%. So regardless of how you present these, present the stimuli, providing there are not two simultaneous targets, it doesn't much matter. You're around about 54, 52% accurate. But when you just look at the AND trials, so you look at that particular subset of trials where two targets are presented at the same time, and your capacity to detect them drops way down to 31%. So there are, following Moray's logic, two results that need to be accounted for theoretically, which I'm writing using a greater than or a less than operation here as a kind of shorthand. The first thing that we saw was that there was a cost, a small but immeasurable cost of dividing attention. You're worse in the OR conditions, either of the OR conditions, than under selective attention conditions, which we can write as OR is less than cell, which means here you're worse when you're dividing attention when two targets can occur when you're monitoring two channels than when you're just focusing attention. But the second finding is that there is a large additional cost of simultaneous detection when two targets both come along at the same time and you have to detect them both at the same time. You're much worse at doing that. So when we write that symbolically as just AND is worse or less than OR. Okay, so according to Moray, there are two relationships that have to be accounted for theoretically, and he argued that neither early nor late selection theory could account for both. What he said is that each of those kind of comfortably accounted for one, but failed to account for the other. So let's try and work our way through Moray's argument. So we've got two relationships, two experimental findings that we would like to explain theoretically. That AND is less than OR, that is, detecting two targets is poorer than just dividing your attention across two channels, and OR is less than cell or worse than cell. Dividing your attention is worse than focusing your attention. So let's see how early selection theory fares. Now, early selection theory wasn't really set up to account for divided attention, but things like the Treisman and Geffen study do have a kind of, this was the TAP task, detect the keyword TAP when it occurs on either channel, does have a divided attention component. And so there seems to be a natural interpretation is that if you're required to divide your attention across two channels, then perhaps you attenuate both channels to some degree, a partial degree, relative to focusing attention where you would attenuate one channel a lot and not attenuate the other channel at all. So that seems to be a sort of natural extension of early selection theory which doesn't do violence to it. So if we make that interpretation, what we would predict? Well, if that's the case, if we say early selection says that when you divide attention, you attenuate both channels to some degree relative to focusing attention, so it would naturally predict that divided attention performance is poorer than selective attention performance, that OR would be less than cell. So we can give early selection theory a tick here. We can say that it does predict attenuation when you divide attention. This is what we find experimentally, so let's give it a tick. However, early selection theory says that attenuation, and the extent that you attenuate, shouldn't depend on the property of the stimulus. It should depend on how you set up to monitor the channels, because the filter is before the limited capacity channel where target identity is extracted. So whether something is a target or not shouldn't determine on how much it's attenuated. So if that's the case, you wouldn't expect any difference in the amount of attenuation with two simultaneous targets as opposed to one target or no targets. So it's not clear that early selection theory can predict this AND deficit. It doesn't say why you should be worse with two targets than with only one. So we have to give early selection theory across there a fail that it's not predicting the additional AND deficit. So early selection theory kind of comes out of this with, at best, a mixed report card. It passes one of the tests, one of the critical tests, but it fails the other one. How does late selection theory do? Well, late selection theory does naturally predict this AND deficit because, remember, according to the way late selection theory works, is that everything excites its representation in the memory system, and then pertinence, so pertinence is relevance, whatever you're trying to do, what matters to the task. Pertinence selects those stimuli which are relevant, passes them through the filter to consciousness. So if the task is to detect targets, then the natural interpretation is that, well, what pertinence is doing is sitting and looking for evidence of targets, and whenever you get some activation which corresponds to a target, pertinence will grab it and try and pass it through the filter. But if the filter has a limited capacity, this is going to get into trouble when two targets appear at the same time. Pertinence attempts to grab them both, but it can only pass one through the filter at a time, and so there is going to be some sort of cost. So the kind of, the slightly kind of facetious visual image is of two big people attempting to get through a narrow door at the same time. So if you've only got one person and you have the door which is scouted side of a person, that person will be able to get through the door without any kind of obstruction or impairment. But if you've got two similar people attempting to get through the door at the same time, then you've got some sort of scheduling competition. And that, in late selection theory terms, can be interpreted as being the cause of the AND deficit of two stimuli identified by pertinence as relevant to the task, but if only one can pass through the filter at a time, then you'll get the AND target deficit. So we can give late selection theory a tick for that because it attributes the AND deficit to selection competition through the late filter. But by exactly the same logic, you would then say, well, if that's the case, if you get deficits when two things selected by pertinence attempt to get through the filter, if you've only got one target at a time, there should be no selection competition. Pertinence is only attempting to grab one target. There's nothing competing with it. So there should be no, if there is no competition, there should be no deficit. So by, again, that same reasoning, we would have to give late selection theory across a fail for that. So what we've got is this somewhat uncomfortable situation where we've got a somewhat complicated pattern of findings which involves two relationships. One of each sits well with one of the theories but not with the other. Now, there's probably a lot more we could say about this. We could kind of argue about Moret's interpretation and whether there are some limitations. What I've tried to do is really kind of give you Moret's logic, and there's probably more that could be said here. But these sorts of findings led people to think, well, maybe we need a different kind of theory. And so in the 1970s, we saw theories based on a quite different set of assumptions, which we're going to talk about now, called capacity theories. So the heading for this part, part of the presentation is structural versus capacity theories. To motivate it, if we think about ways in which attention can limit performance, ways in which our attentional system can limit how we process and how we respond to stimuli in the world. Now, we have talked at length about one way, which is via filtering. So filter theories basically says that you've got a limited capacity channel that can't process everything, so you've got a filter which limits the information from the world that gets passed through in the limited capacity channel. These type of theories are often referred to in general or generic terms as structural theories because they attribute the attentional limitations that we observe to some particular feature of the processing system. That is the filter and the properties of the filter. And we've talked at length about the properties of the filter. And they're often also referred to colloquially as bottleneck theories because they can be kind of visualised as a kind of a narrowing or a constraint of the processing system, like the narrowing of the neck of a bottle. So initially, in the body of the bottle, you have all stimuli processed at once, but at some point there is a kind of constriction or a narrowing, which is why they're often called bottleneck theories. So they have, unfortunately, no connection with slide guitar at all. For those who might be disappointed. If not, we can move on. Filter theory, Broadbent's original filter theory, early selection theory, and late selection theory can really all be thought of as structural or bottleneck theories. Early selection theory saw the structural limitation or the bottleneck imposed by the filter as at the point of getting into long-term memory. Late selection saw the bottleneck at the point of getting out. So that's one way that attention can limit performance, and we've talked at length about that. But there's another completely different way of thinking about these limitations, which goes back to the idea that we introduced at the outset, that information processing is mental work, it's neural work, it's metabolic work, and that mental work of this kind requires us to activate neural structures, which are ordinarily dormant or quiescent. And we start with the proposition that maybe we just have a limited capacity to activate structure. We may be able to do that in a very flexible way, but we just limit it in the total amount of neural structure that we can activate at any one time, because we're limited in the amount of metabolic work, of stored blood sugar that we can burn through. So that idea became very influential in the 1970s as the result of the work of Danny Kahneman. Kahneman is now a very famous guy because he won the Nobel Prize for Economics in 2001 or 2002 for his work on behavioural decision theory. So one part of Kahneman's work was looking at theories of real-world decision-making with Amos Tversky, and that work and the associated theoretical background, particularly a theory called prospect theory, it was seen as pivotal to the development of how people make real-world decisions, and became very, very influential in economics, and was actually recognised by a Nobel Prize in economics. And more recently, Kahneman is also the author of the popular book Thinking Fast, Thinking Slow, which is a version of a two-system theory of cognition. But his early work, the work that he first became known for and first became influential for in the 1970s, was his work on attention and proposing capacity theory. So Kahneman was the first one who said, rather than thinking about attentional limitations in terms of bottlenecks or structural limitations within the processing system, let's think about them in terms of a limitation on the total ability to activate neural structure, to do mental work, to process stimuli. And a good way of kind of visualising what Kahneman is proposing is to think of capacity as being a kind of hypothetical reservoir of allocatable stuff, the ability to activate neural structures. So we can kind of represent capacity as a single store of available stuff which can be allocated across tasks. So in a focused attention task where we're told it's really important that you do task 1 well, task 2 doesn't matter so much, what we would expect is that people would allocate most of their capacity to task 1 and only whatever residual is left over to task 2. So task 1 performance would be good and task 2 performance would be pretty ordinary. But alternatively, we can say, well, both task 1 and task 2 are important, emphasise them both as important, so people would then divide their attention or their capacity equally between those two tasks, and so we might expect to get intermediate performance. Now, what's new here and what is the hallmark of capacity theories and what differentiates them from the earlier structural theories that we've been talking about is this new idea of flexible capacity allocation. The idea is that we can be very flexible in the way we can allocate capacity to simultaneous tasks. So here is a relatively contemporary study by Dave Strayer and colleagues looking at the interfering effects of divided attention. This is a nice real-world study, or ecologically valid study, as we might say, which has received a lot of media attention because it's dealing with the very topical issue of the effects of talking on a mobile phone on driving. So this is a pretty simple study. It's basically just getting people to perform in a driving simulator, in a real-world task where people have to respond to obstacles, including stopping at stoplights, either just doing the driving simulator task or talking on a mobile phone, or a cell phone, as it's called here, as they call them in America. The results here are very straightforward. It simply shows the fraction of red lights missed, so this is a measure of performance accuracy in the left-hand panel, and the reaction time to respond to obstacles, to red lights, either when people are just doing the driving task alone or talking on a mobile phone. And as you can see, both accuracy and reaction time take a hit. It's not huge, it's not gross, but when people are just doing the driving task, they're missing around about 2% of red lights. As soon as they're on a mobile phone, they're missing around about 7%. So, by and large, they're responding accurately to most of the red lights. But of course, the regrettable reality of driving is that you only have to miss one red light for a catastrophe to occur. Likewise, the increase in reaction time, it's not long. So these are relatively long reaction times because these are kind of, these are gross motor times, time to hit the brake, which is, with no mobile phones, about 550 milliseconds, and it's lengthened by about 100 milliseconds. Now, again, the change is not long. The change is not in reaction time is not long, but if you think 100 milliseconds, a tenth of a second at 60 kilometres an hour, you will cover around about 1.7 metres, and so that difference may be the difference between either being able to stop or not stop for a person. So that's the kind of result that capacity theory kind of naturally accounts for. It doesn't say that there is any kind of bottleneck. You're doing quite different things. You're processing visual stimuli on the one hand and responding by pressing brake pedals, and talking on a mobile phone at the same time. According to capacity theory, what produces this kind of deficit is just the fact that both of these tasks are capacity demanding, and your sharing capacity, talking on a mobile phone, takes capacity away from the driving task, and the driving task, it doesn't collapse completely, but it becomes measurably worse on certain key indicators. Here's another example, a more kind of laboratory-based example of this from Lee et al. Again, showing the use of a kind of dual task technique to study capacity allocation. In this case, they asked people to do what they called a central and a peripheral task. So the central task involved looking at an array of disordered letters, disordered in their orientation, and to say whether they were all the same or different. In this case, you've got a bunch of T's and an L, so the correct response was different. So this was a deliberately demanding task. And at the same time, people were asked to also do a peripheral task where various little stimuli were flashed up in the visual periphery. So people were monitoring this central stream and while flashing up a task in the visual periphery, and the task was then to determine, and there were two versions of that. In one, people were asked to, when they were presented with a brief photo of a scene, and they were asked to determine whether an animal was present. In this case, it's a polar bear on an ice floe, so the response would be yes. The other, to determine the organisation or the phase of a disk composed of a red half and a green half, and to say whether the red half was on the left or the right. Now, surprisingly, perhaps, the disk task is a harder task, we know from various criteria, is a harder task than the animal task. People are capable of processing the gist, the so-called gist of scenes very rapidly, and are able to do this kind of polar bear task, this animal present task, very quickly and efficiently, whereas reporting the phase of the disk requires attention. And so what you see on the right is how accuracy of the peripheral task changed when it was done along with the central task. And as you can see, the animal present task, when it was performed along with the central task, accuracy was still very high. So people were still up near 90% correct, even when performed with this demanding central task. But the phase task, which people could do well on its own, accuracy went down to, this is around 50%. When it was performed as a second task. So this again kind of nicely sits with this capacity allocation view, the idea that the central task, the letter task, soaks up most of the available capacity and only leaves a small amount of capacity for the a small amount of capacity for the second task, the peripheral task. If the peripheral task is not an attentionally demanding task, if it's an easy task, then people can still maintain a high level of accuracy. But if it is an attention-demanding task, then it shows a very considerable hit. Let's do one more little example, and I'll just see if I can get this. This is a capacity explanation of attentional blindness. Now, here is inattentional blindness. Now, here is a very famous YouTube clip, which many of you have seen, so this won't come as a surprise to many of you, but it might to some. So basically what you're going to see is a bunch of people tossing a basketball backwards and forwards. Some of them got white T-shirts, some of them got left T-shirts, and the task is to count the number of passes made by the white team only. Okay, so ignore the passes made by the black team and just count the number of passes made by the white team only.
How many passes did you count?
Regardless. How many noticed the gorilla?
Passes. But did you see the gorilla?
Did someone... Okay, right. So a gorilla wanders through, beats his chest, and then exits.
This video is from research by Daniel.
Yes, thank you, Daniel. We appreciate your contributions to attention.
It is available for use in talks, training, and teaching on DVDs from VisCog
Sorry, I'm
Productions.
going to have to cut your pitch off, Daniel. Okay. That is a phenomenon called inattentional blindness. And yeah, it's very striking. The way this works, of course, is because you're invited to perceptually segregate the world into black figures versus white figures, which we're capable of doing. We're capable of attentionally selecting either on the basis of tone or colour. As the result of focusing attention and doing something attentionally demanding, keeping track of the number of passes, many people wholly are unaware of the black gorilla that wanders through. Obviously, if it had been a white gorilla, the majority of people would have noticed. So this is an example of inattentional blindness. Here's a more controlled laboratory demonstration of the same thing by Nili Levy's, from Nili Levy's group. In this case, the attention-demanding task is to monitor two arms of a cross. So a cross which is flashed up very, very briefly. So it's got a blue arm and a green arm, and the task is just to judge whether the blue arm or the green arm is longer, and people do a sequence of trials. And so as you can see in this first panel on the left here, the blue arm is longer here, the green arm is longer. But then, after a sequence of such trials, another stimulus, like a bright rectangular box, is flashed in the visual periphery. So it's flashed up at the same time. It's not hard to detect perceptually. So it's not at low contrast, it's not presented very, very briefly. So it's a very obviously visible stimulus, but nevertheless people don't detect it. Now, once again, capacity theory provides a nice account of all of this. The idea that the line length detection task is a perceptual discrimination task. It's attention demanding. It tends to soak up all of the available capacity, and even an easy task like detecting a square is performed at very low levels of accuracy. So the idea is that the central task soaks up all of the available capacity. There's little or nothing left for this square task, so people are unaware of it. So people are unaware of this just as they're unaware of the gorilla. So these are findings which were stimulated by capacity theory. Capacity theory says, well, let's look at how well and what are the limits of people's ability to divide their attention across tasks, and we can discover these sorts of relationships, these sort of surprising relationships in which stimuli which ordinarily should be easy to detect, easy to report, are not reported by virtue of the way we've allocated attention. Now, I'm running slightly behind my schedule, but let's take our mental health break now, and I will try and deal with the timing issue as I go along. So 5-minute mental health break at this point. Okay, folks, can we make a start? I just need to catch up on a little bit of material. So, before getting on to the second half, which is really visual attention, and the subject of visual attention, just a few more comments on the subject of capacity theory. I gave you some examples of findings, interesting findings, including inattentional blindness and performance decrements with divided attention, which kind of sit very naturally within a capacity theory framework. The idea that we've got a finite pool of capacity. If we allocate most of it to an attentionally demanding secondary task, then there is only a little bit of capacity left over, and that leads to poor performance on another task done concurrently with it. If that task is a difficult capacity demanding task, it'll take a bigger hit than if it's an easy task. Nevertheless, that might strike you as a bit kind of loose and theoretically vague and unsatisfying. And so the question is, can we study capacity a little bit more systematically? Do capacity theories make any distinctive predictions? And one proposal, one interesting idea, which capacity theory gave rise to, was the idea that we can study trade-offs between two tasks, just of the kind that we've talked about, in a systematic way by getting people to vary the fraction of their attention or their capacity to two tasks. If capacity is a flexible, allocatable thing, as the theory proposes, then people should be comfortable devoting 50% of their capacity to one task, or 80% of their capacity to one task and 20% or the other, and so on. And so the idea comes that we could derive a theoretical function by getting people to do two tasks. Speaking generically, let's just call them task 1 and task 2 at the same time, but instruct them in different ways, either to devote 100% of their capacity to task 1, in which case we would expect task 1 performance to be really good and task 2 performance to be at floor, or 80% of their capacity to task 1 and 20% of their capacity to task 2, in which case we might expect some deterioration in task 1, but task 2 would be better, or to devote 50% of their capacity to either, in which case we'd expect kind of moderate performance on both, or 20% to task 1, in which case pretty poor task 1 performance and good task 2 performance, and finally 100% of their performance. And so the idea, which really follows from capacity theory's idea that capacity can be flexibly allocated, is that there should be some sort of graceful change or gradual change or graceful degradation of performance as the availability of capacity is reduced. It shouldn't be an all or none thing, like the filter is switched to this channel or it's not, a la Broadbent. So Broadbent's theory was the exact opposite of this. But we would expect that if this makes any sense, that that people would think this is a sensible thing to do when we ask them to do it, and we would see this kind of graceful allocation of performance. And so the theoretical curve that we would trace out as we observe people's performance in different conditions, as they vary the fraction of their capacity devoted to the two tasks, is called an attention operating characteristic, or AOC for short. But note this, of course, I've just kind of drawn a curve in an abstract way going through this in this space, which describes task 1 and how task 1 performance varies as a function of task 2 performance. But you could draw lots of other different curves through this space as well. What curve that you would find is really an empirical question which you would have to discover experimentally. But we can ask the thought experiment, or do the thought experiment, saying, what if we did this and we found that, say, the 50-50 point was way up here at the intersection of the horizontal dashed line and the vertical dashed line? So if we did this task and said devote equal capacity to task 1 and task 2, and we found that the 50-50 point was way up here, what would we conclude? Well, clearly what this would be telling us is that you're just as good doing two tasks at once as you are when you're doing either of them alone, which would suggest that that either one or both of them is not drawing on the available capacity. So the idea that by studying the kind of empirical attention operating characteristic obtained in this way, you can learn something systematic about how people allocate the capacity. Let me just give you one example of a comparatively recent study that attempted to do this. This was from Anne-Marie Bonnell's group in Paris, working with someone called Hafter in 1998. And what they did was got people to do two tasks, an auditory task and a visual task. So again, they were looking at how performance on an auditory task and a visual task traded off against one another. And they looked at two versions of each of these tasks, one of which they called a detection task and the other they called a discrimination task. So the detection task just involved detecting a weak stimulus against a blank background. So in the visual version of that, that was just a blank screen. On no trials, there's nothing there, nothing to be seen. On yes trials, on detection trials, there was a very weak, faint patch of light. So the task was just to say, yes, that patch of light was there or not. The auditory equivalent, there was a continuous auditory tone background with a brief increment in the auditory intensity, so a brief increase in auditory intensity, an analogue of this brief faint disc in the middle, and again the task was to say I detected it. So that was the detection task. The discrimination task was one in which there was always a stimulus present, but either it was a brief and faint increment in the luminance, so the disc in the centre was a little brighter, or it was a little darker, and people had to say it was either brighter or darker. And they called that a discrimination task. And the auditory task was again an analogue of that. There was a brief increase in the auditory intensity or a brief decrease. And these were very brief stimuli. They were 20 milliseconds, so right down at the threshold of detectability. And this shows what they found. So these are their experimental attentional operating characteristics for the discrimination task. These are the green symbols, and the detection task. This is the red symbols. Now, what's been plotted, the performance measure is not percent correct, but a performance measure from a theory of decision-making, how people make decisions about brief stimuli, called signal detection theory, which we'll talk about a lot next year. And the virtue of signal detection theory is that it takes account both of correct detections and of errors, and it produces an accuracy measure that takes into account both correct responses and errors, called D prime, which is really a D with a little apostrophe, which in mathematical notation is called D prime. So for our purposes, we won't worry about how D prime is defined. Just think of it as a better mousetrap, a better measure of detection or discrimination accuracy. So what they've done is plotted D prime as a measure of accuracy for audition on the y-axis against D prime for vision, for the visual task, on the x-axis. And in terms of the way that D prime scales, you can think of a D prime of 2 as being a moderately difficult task, a D prime of 1 of being a fiendishly difficult, next to impossible task, and a D prime of 3 of being a fairly easy kind of task. Now, what's interesting about their results is how very different the attention operating characteristics for these two tasks, two apparently quite similar tasks, appear. For the discrimination task, we get the nice, smooth AOC that we would predict from a capacity sharing model. So if both the visual and the auditory task both drew on a common source of capacity and that was shared in various proportions as people were instructed to devote 100%, 80%, 50%, 20% or 0% to the auditory task, then we would get this nice kind of semicircular or quarter-circular AOC. Now the detection task is the data are a little bit ragged because D primes become a bit hard to estimate reliably when the task gets too easy. But if we squint our eyes a little bit, we might be prepared to say, well, these points for the divided attention tasks, the 50-50 task, the 80-20 and the 20-80 tasks, all are tending to be congregating around the intersection of the horizontal line through the single auditory task and the vertical line through the single visual task, which by our logic would be saying, well, this task doesn't seem to be drawing on capacity very much, if at all. By and large, accepting the variability or the noisiness of the data, it looks as though people can do two detection tasks just as well as one. So I'm showing this to you mainly to show you that the AOC method gives you a systematic way of studying trade-offs which is consistent with the capacity theory worldview, that capacity is something which is flexibly allocated and can produce these gradual changes in performance. And I don't want to dwell on the meaning of this too much, but you might say, well, you know, why are these two tasks different? And one plausible interpretation is that the detection task is controlled by stimulus transients, by flashes of light or blips of sound, and those sorts of transients can be detected pre-attentively outside the limited capacity system, and they're used to shift attention around. So we call that shifting of attention, which is what we're going to talk about in just a moment, attentional orienting. And so this would suggest that attentional orienting by these briefly flashed stimuli may be largely pre-attentive and not draw on capacity, whereas identification, actually determining what the thing is that an increment or a decrement, to discriminate between them, may require their limited capacity system. So this is an example of the kinds of insights that capacity theory can potentially give us. I'm going to draw a line under capacity theory at this point, and the capacity theory story. As I said, it was very much a 70s and to some degree an 80s theory, and we've had a lot of time to think about it and to think about its strengths and weaknesses. It has some obvious strengths, one of which are the kinds of new experiments that it led to. And I've tried to give you a little bit of a sampling to give you a flavour of those, which are these interesting experiments on how people trade off performance in divided attention tasks and show that under some circumstances people can trade off fairly well, on others very, very poorly. So we get phenomena like inattentional blindness, which shows a complete failure to trade off. One of its shortcomings is there is an element of theoretical vagueness. It always seems to be possible to come up with some sort of capacity theory explanation post hoc if we say, well, why did that happen? And it's always easy to say, well, this task is more capacity demanding than this one, and this is the way people were allocating their capacity. In other words, capacity theories are very, very difficult to falsify. And compare that with Broadbent's theory that we talked about last week, which was decisively crisp in its predictions and gave us something that we could experimentally falsify in a decisive way. Capacity theory is one of those slithery theories that's kind of capable of sliding around and always saying, well, that's because that's how the capacity was allocated. We can make capacity theories mathematically more precise using signal detection theory, but that's really a topic for third-year perception, memory and cognition. So let's draw a line under that, and in the last half of our last half, talking about a new topic, the control of visual attention. So there are some relevant readings from Styles, 2 chapters, The Nature of Visual Attention and Visual Attention, and again a little section from Goldstein, which is relevant. And again, I'm now coming up to the 1980s. You might be surprised, you might have been surprised last week when we were talking about attention, that all of the early work on attention focused exclusively on audition. So last week we talked exclusively about dichotic listening type studies. We talked about visual attention a little bit in the last 15 minutes, but again a lot of what we talked about today was auditory. And that may have struck you as strange because we are such a visually dominant species. Our visual system is by and large, is far and away our most important sense. So you might wonder, why did psychologists spend so much time focusing on audition rather than vision, given the biological importance that vision has for us? And there are a couple of reasons. One is a technological one. People tend to do experiments using the technology that they have available, and the kinds of experiments that they do is determined by that technology. And dichotic listening studies could use technology which was pretty mature at the time, largely stereo tape recorders. Stereo tape recorders were developed well before programmable visual displays, which really only became available towards the end of the 70s, early in the 1980s. And so one of the reasons was that the technology was there for doing those sorts of studies. But there is also another deeper and slightly more principled reason, which is as soon as you're dealing with visual attention, you have to take into account the problem of eye movements. Now, as you know, as we move around our natural environment, when we're confronted with interesting stuff, such as flashes in our visual periphery, which is telling us that something has changed or something unusual, something that might require our attention has happened. And our natural response to that is to produce an eye movement, a saccadic eye movement. These are rapid ballistic eye movements, which serve to bring stimuli that were in our visual periphery into our central visual field. And there are lots of perceptual benefits to doing this, as of course you know. Our central vision, our foveal vision, the 2 degrees at the centre of our visual field, and 2 degrees is about the angle subtended by your thumb as you hold it out at arm's length. So if I hold my thumb out at arm's length, it pretty much, and close one eye, it pretty much just obscures the head and the body of someone who is sitting midway up in the lecture theatre. So that area, yes, I'm using my thumb to obscure you, and I hope you won't take that amiss. So that area occluded by your thumb at arm's length is about 2 degrees of visual angle, and that's the size of your fovea. So the fovea is where all the kind of visual good stuff is. This is where you've got the maximum concentration of cones, which you need for resolving colour. So pretty much all of your fine colour vision is located in the fovea, and this is where all of your ability to resolve fine spatial detail also resides, because if we look at the primary visual receptors as they're spread out across the visual field, they're very, very small in central foveal vision, and they get progressively larger as we move out into the periphery. So all of that's terrific and wonderful and adaptive and interesting if we want to study perception. But obviously, if we want to study attention, it's all just a nuisance. We're not interested in the fact that you see things better in peripheral vision in central vision than in peripheral vision. If we're interested in what's the effect of attention, we need to be able to control those differences. What we're actually interested in is a covert attention, that is, movements of attention independent of eye movements. Or because American usage has now completely taken over the world, covert attention. And by that we mean shifts of attention which occur independently of eye movements and which can occur without them. And those shifts of attention are called attentional orienting. And so the difficulty, of course, is if you want to study them and study them systematically, you need some technology for monitoring eye movements and determining when people have made an eye movement and rejecting those trials and only looking at those trials where they have focused attention. So that is, I think, why, that's a kind of deeper reason why studies of visual attention only seriously got going in the 1980s, when technology for doing eye movement monitoring became widely available in cognitive laboratories. Now, one of the most influential and important ideas in this area was due to someone called Michael Posner, working at the University of Oregon in the United States, and he proposed not a model, but a metaphor, an evocative and influential and useful metaphor of the spotlight attention, where he likens these shifts of covered attention to a moving spotlight. The analogy is that you're invited to think of is taking a torch and shining it around a darkened world. As you shine the torch around, the beam of your torch will illuminate an area of space. So whatever falls within the beam of the torch is seen well, it's seen clearly. Whatever is outside the beam of the torch is either not seen at all, if the world is very dark, or seen only somewhat poorly in a reduced or degraded way if it's dimly lit. And so Posner likened the movement of spatial attention covertly around the visual field to the action of shining a spotlight or a torch selectively around the field. So you can see the basic kind of claim and the implication of this is that if we've got two stimuli, two regions of the field labelled A and B, if I shine my torch on region A, there will be some benefits. There will be some sort of enhancement or improvement in my ability to process whatever falls within the beam of the spotlight relative to B, where performance there will be degraded or not processed at all. And this is just supposed to, the claim is that this is just an attentional phenomenon. It will happen even if I'm keeping my eyes nicely fixated in the middle of the display, simply as the result of moving my attention around. Now, what this is really doing, what his Posner's spotlight metaphor is doing, is expressing a familiar idea, that is the selective limited capacity of attention, which we talked about all the way back to Cherry and Broadbent indeed, but in spatial terms. And so a lot of the kind of claims and implications that follow from it would be familiar. Now, as well as providing us with a productive, evocative metaphor for thinking about visual attention, Posner provided us with a wonderfully flexible experimental technique which has been very widely used to actually study it, the so-called spatial cueing paradigm, which can be spelt with or without an E depending on which side of the Atlantic you're on. And so the idea is straightforward, is just on any trial you present some sort of cue which encourages people to direct their attention to that location. So you present on each trial, before the stimulus, a cue which encourages people to attend to either location A or to location B. If the cue directs attention to move to a location A, then you can say when people are attending to location A, are stimuli at A processed faster or more accurately than stimuli at B. Lots of ways of doing this. This is probably the most basic way. Posner originally used this and applied it to the very simple task of just detecting spots of light. Now, spots of light, they weren't down near threshold, weren't down near the very visual threshold. They were sort of visible and easy to see. But he was interested in saying, does attention nevertheless have a role in processing those stimuli? So in the most basic version of this, you might have a blank screen with a fixation cross, and people are instructed, they're encouraged to keep their eyes fixated on that cross for the duration of a trial, which people are in fact pretty good at doing. And if you're worried about timing, you can use an eye movement monitor. So typical eye movement monitors bounce a small infrared signal off the cornea of the eye and measure the reflections. And as the eye moves around, the reflections of the infrared signal bounced off the cornea change. And so by monitoring those, you can determine where the eye is looking. On either side of the fixation cross are a couple of designated locations where stimuli can occur. The timing of an experimental trial in this sort of task is that we present a cue, and there are various cues. We'll talk about these cues as we go along. Here, they can be as simple as just an arrow. So an arrow is a kind of a symbolic cue which says direct your attention to the box on the left, and so the cue can either point to the left or the right, and attention is instructed to shift to the left or the right accordingly. We present the cue and then we wait for an interval, a designated interval, before we present a stimulus that the person has to respond to. Now that interval in the cueing world is very, very important. It's so important that we give it a special name. We call it the stimulus onset asynchrony, or SOA for short. So the SOA is the time elapsing from when we present the cue to when we present the stimulus. And typical SOAs of theoretical interest in this world are typically on the order of 100 milliseconds to 300 milliseconds. So somewhere between a tenth of a second and a third of a second. And then when we present the stimulus, we start the clock and measure response time. Now, the way the spatial cueing task works is that, as I said, we use cues to instruct people to direct their attention to a particular spatial location, but we're also interested in what happens when they're not attending to a location. So the way we do that is that we allow the cue to be informative, but not perfectly informative. So a typical way of doing this is that on 80% of trials, the stimuli to be detected, in this case a spot of light, a white spot, a bright spot, occurs at the cued location. So the cue is an arrow and the stimulus to be detected occurs at the cued location, but only on 80% of trials. And such trials are called cued or sometimes valid trials. So what we mean by a valid trial is where the cue validly or correctly predicts the stimulus. And we can contrast that with the remaining 20% of trials in which we cue a location, but the stimulus occurs in another location. So here we've cued the right box and the stimulus occurs at the left, in the left. And so this is variously called a miscued trial or an invalid trial in which the cue is not predictive. Now, because the cue is reasonably informative, so it's predictive on 80% of trials, people are encouraged, they're motivated to use the cue and not just totally ignore it. But because it's only imperfectly predictive, it allows us to compare what happens at cued and miscued locations. The assumption, of course, being that attention has been switched. The spotlight has been moved to the cued location. And to give us a kind of baseline for comparing performance, often we can throw in some neutral trials in which the cue is uninformative. Now, we could leave the cue out completely, but that's not a good idea because the cue's giving us timing information. So one way of doing this would be to present two arrows which cue both locations, and the stimulus can occur on the left on 50% of occasions and on the right of 50% of occasions. So this is a kind of a slightly kind of coarse mock-up of what this would look like, but you get an idea. So a fixation point with a couple of boxes, a cue, in this case it's just a bar marker rather than an arrow. the cue is extinguished, a target to be detected is presented. In this case, this is a valid trial. You start the clock at the time of the stimulus and stop it when the person responses. You can contrast this to an invalid trial. Again, we present a cue, again a bar marker, but now the target occurs at the other location, and so we can compare performance on those two conditions. If we do this, we find this very, very interesting pattern, again using the neutral condition as a baseline. So this is from one of Posner's very early studies, Posner, Nissen and Ogden in 1978, but there have been vast legions of experiments, thousands of experiments who've used variants of this method, because it's very flexible and it can be adapted to all sorts of settings. But in the simplest context, the one I've shown you of just detecting a spot of light, what you can see is if we compare response time to detect the spot of light on valid cues, that is correctly cued trials, performance is faster than when the cue is uninformative. And so that is referred to as an attentional benefit. The fact that you're faster, response time is faster when the cue correctly identifies the location of the target. And symmetrically, on miscued trials, when attention has presumably been directed to the wrong location, you're slower than on neutral trials, roughly symmetrically slower. And so this slowing, when attention has been directed to the wrong location, is referred to as an attentional cost. Posner's original interpretation, using his spotlight of attention metaphor or model, was that the costs and benefits are due to switching times. This is actually very much a kind of Broadbent version, the Broadbent type theory. Broadbent's filter theory says that there were costs of switching the filter to the left or the right channel. Posner was proposing something quite similar, but in visual spatial terms. So his idea was that in order to complete the task of processing the stimulus, you actually have to switch the spotlight of attention to the stimulus location, much as Broadbent said that in order to be able to recognise something, you have to switch the filter to the associated channel to read it into the limited capacity channel. This is a very similar sort of idea. And so his idea is that to complete the task of processing the stimulus, you have to switch the spotlight, you have to shift the spotlight to the correct location. If you validly cue the stimulus, the spotlight will have already shifted to where it needs to be by the time the stimulus is presented. So there are no switching costs because you're already where you need to be, and so that gives you an intentional benefit due to the neutral condition. Conversely, on miscued trials, where the spotlight has been sent off to the wrong location, and then a stimulus comes up, in order to be able to complete the task of responding to that stimulus, you have to switch the spotlight back, and so it has to come all the way back from the wrong location where it's been reallocated to the correct location, and that gives you attentional costs. So that's a kind of switching account. It's a spotlight, a moving spotlight account of the symmetrical costs and benefits that you see in the queuing paradigm. You can, with the wisdom of capacity theories, which we've just been talking about, come up with a capacity theory account which doesn't involve any kind of particular switching during the course of the trial. And if we said, well, what would capacity theory predict? Capacity theory would say, well, response time depends on how much capacity that we allocate to a location, and we can allocate our capacity thinly, so we can concentrate some of it at one location, at the probable location of the stimulus, and withdraw it from the other location, the improbable location. And if that's the case, when the stimulus actually does appear at the cued location, because that's where most of our capacity has been allocated, will be fast. If it occurs at the other location, where there is relatively little capacity, will be slow. So both of those accounts kind of work theoretically, and they're somewhat hard to test between, and I don't propose to try and do it here, and I hope that won't leave you too bitterly disappointed. What I want to do in the last 10, 15 minutes is to instead use the queuing method to look at an interesting substantive question in terms of how many different attentional control systems do human beings have. So we're motivated to ask that question, why it's a theoretically interesting question, is that if we think about how our attentional system adapts us to the natural environment, how we are able to get about the world, do things in the world without coming to grief in various ways. And we have to be able to control our attention in order to do this. We have to be able to shift our attention in a top-down, purposive fashion if we're going to engage in purposive, goal-directed behaviour. We have to be able to say, OK, given what I'm attempting to do now, I'm going to attend to that thing to the exclusion of others, and so I have to be able to voluntarily allocate my attention to whatever stimulus is concordant with my current goals. But on the other hand, we have evolved in a hazardous, changing environment, and we need to be able to respond to changes, some of which may be threatening, which occur unexpectedly in the environment around us. So in other words, we need a mechanism for rapidly disengaging our attention and reallocating our attention in response to sudden changes in the world. Those sorts of changes, using the terminology we introduced last week, are bottom-up. So in other words, a normal attentional system kind of needs a balance of top-down and bottom-up control mechanisms in order to be able to function. If we don't have both of those, we're going to end up displaying very dysfunctional, maladaptive behaviour. We can find clinical patients who show deficits both of failures to focus attention and failures to disengage attention. And in the last lecture, we'll say a little bit about the neuropsychology of attention. But let's just talk about behavioural experiments. So the claim that I want to spend a few minutes discussing is how many attentional control systems do we have, and can we distinguish them experimentally? And my claim is that we can, using two different kinds of cues. There's two different ways that we can shift attention, we can cue attention. One is the way that we've just talked about, using a symbolic cue, a central symbolic cue like an arrow. Now, an arrow is a cultural artefact. It has meaning. It has a learned meaning, just like language. We learn what an arrow is, and we learn that an arrow should be interpreted as a pointer, indicating a particular direction. But all of that, when we see an arrow and we interpret it, requires some intervening cognition. Of course, it's very fast because we're all really familiar with arrows. We've seen lots of arrows during our daily lives. But nevertheless, it requires some interpretation in order to be able to be used to direct attention. So that's one kind of cue. And so the idea... let me contrast the other one first. Now, the other kind of cue tries to bring into the laboratory the idea that one of the things our attentional system needs to be able to respond to is sudden changes in the environment that occur in our visual periphery, like flashes of light. So another way we can cue attention in our cueing paradigm is just to introduce a flash of light in the visual periphery at one location or another. Various ways you can do this. One way is just to brighten the boundary of the box that denotes one of the stimulus locations very briefly, like a brief 60 millisecond flash of light. So the claim is then that we have two different attentional control systems, a top-down voluntary one and a bottom-up automatic or reflexive one, and that these two systems can be selectively activated by using the right kinds of cues. The alternative, somewhat jargony terms for these two systems are the endogenous system for the voluntary system and the exogenous system from the reflexive system. So endogenous from endo, meaning from within. So in other words, attentional shifts which are controlled from within in a top-down voluntary way. Exo, meaning from without, shifts of attention which are controlled externally by stimulus in the environment. So the claim is that we can, by using these two different cues, we can identify and characterise two separate attentional orienting systems. I have 3 bits of evidence which I will try and get through. One is looking at the time course, that the two attentional systems have very different time courses, which we can identify using these two different types of cues. So what we're interested in now is characterising the overall magnitude of the cueing effect, which I'm defining as the difference between cued reaction time and miscued reaction time, or in other words, valid reaction time and invalid reaction time. So we've just saw from the Posner-Nissen and Ogden study that you're slower on invalid trials than valid trials. So let's define the cueing effect as by how much faster you are on valid than in invalid trials, algebraically by the mean reaction time on invalid trials minus the mean reaction time on valid trials. Now, if we're plotting this difference, this cueing effect, as a function of the SOA, that is the time elapsing between the stimulus and the cue, what we find is that peripheral flash cues and central symbolic cues have quite different time courses. If we use a central symbolic cue, the cueing effect is quite slow in cognitive time to build up. It takes about 300 milliseconds to get to its maximum, which is slow. That's a third of a second. But once it's there, then it stays there. So in other words, when we use central cues, the cueing effect is relatively slow, but it's sustained. However, if we use a rapid flash peripheral cue, we get a very different profile, that the cueing effect reaches its maximum very, very quickly, within 100 to 150 milliseconds, so a bit more than a tenth of a second. But if we wait longer, then the cueing effect starts to dissipate or evaporate. And if we wait too long, it drops back to 0. So in other words, the cueing effect that we get with peripheral cues is fast but transient. So this is consistent with the idea of two systems that have quite different time courses. A slow, centrally controlled system that requires us to interpret the stimulus in order for the cue to have an effect, that involves some amount of intervening cognition, and that takes time, versus a fast peripheral system which responds automatically and pre-attentively to changes in the environment very, very rapidly and produces its maximum effect with just over a tenth of a second, just over 100 milliseconds, but then which rapidly dissipates. So that's one bit of evidence. The second bit of evidence was a bit of was an experiment by John Giannides in 1981, who interpreted the cueing effects using capacity theory. And his idea is that if we think about these two systems in capacity terms, the voluntary orienting system requires cognition. It requires us to interpret the cue and to do something in a voluntary way in response to it, like shift our attention. So Giannides said that's likely to take capacity. The interpretation and the response of a cue, of a central cue, is likely to require capacity. Whereas a peripheral cue is supposed to be a fast automatic thing which is triggered outside your ongoing cognition by the occurrence of a flashed stimulus. And that's likely not to require capacity. So he said one way of testing this is by getting people to do the attentional orienting task while they're doing another capacity demanding task. In this case, a memory task where they were required to hold a set of letters or digits in their short-term memory system. So this shows the way he set his task up. People did a memory task where they were required to hold material in their short-term memory system, which was designed to draw capacity away from the orienting task, and the orienting task was designated as the secondary task, which only got the capacity that was left over. And what he showed is that the voluntary orienting was slowed by memory load, so responding to a central symbolic cue was slowed by memory load, but reflexive orienting, responding to a peripheral cue, was not. So this was again consistent with the idea of different capacity demands of the two systems. Last bit of evidence is what you find with peripheral cues if you really prolong the SOA. So we've said that when we use peripheral cues, we get a fast transient attentional effect, which peaks somewhere around about 150 milliseconds, but then it starts to dissipate. And so if we wait too long, the cueing effect completely vanishes. What happens if we wait a really long time, like 300 milliseconds? Well, remarkably, if we prolong the SOA, so we present a cue and then introduce a long wait before the stimulus, the cueing effect can actually reverse. It can go negative. So here I've shown that this curve, which plots the difference between invalid trials and valid trials, and so it will be positive to the extent that you're faster on valid than in invalid trials, but at very long SOAs, it goes negative. In other words, what this means is that you're actually faster for invalidly cued stimuli than validly cued stimuli, which is strange and remarkable. And this phenomenon is referred to as inhibition of return. So the terminology inhibition of return says that if you have cued attention using peripheral cues and activated the involuntary system, that will lead to a rapid attention shift to that location. But if nothing interesting, no stimulus occurs at that location, attention wanders away, to be anthropomorphic about it. And it's basically said, nothing of interest to me here, and once attention has wandered away, then it's hard to get back. And so this is what's termed inhibition of return. Now, had I had a little bit more time, I would have talked a little bit about the theoretical significance of inhibition of return. People have speculated about what inhibition of return is good for and why the cognitive system actually exhibits it. And the argument is, well, maybe it helps us search complex visual scenes in an efficient way. What I'll just say for today is that this additional phenomenon, the fact that we find inhibition of return only with peripheral cues, only with the reflexive orienting system, is our third bit of evidence for two separate attentional control systems. So given the lateness of the hour, I will leave it there and perhaps pick up some of the conclusions next time we meet. But what I've shown is, I think, the functional utility of this cueing mechanism for this cueing paradigm for asking and answering interesting questions about how visual attention is controlled. So thank you. I hope it's not hailing or raining or doing anything foul out there, and that we all have a dry trip home.
Asked about the late selection that you mentioned.
Yep.
So the late selection, it accounts for n less than or, because there's competition, because there's simultaneous. So it has competition too.
Yep.
But doesn't explain or less than selection because there's more.
Because there is no competition. So basically it says that you should see poorer performance when there are two things competing.
Yeah.
So when they're both selected by pertinence, so they're both trying to get through the filter. But if that's your interpretation, then providing there's no competition, so if only one thing is selected by pertinence, there should be no poorer performance, so you shouldn't be worse in or than in
So
self.
this should be, according to Lee's side, this should be equal.
They should be equal,
Okay. For this early selection,
Yep.
it doesn't account for n less than or, because if it's equally attenuated, then n equals to or should be equal.
Yep, that's correct.
Okay.
Yep, good. Well, because that's a complex study and it's hard to kind of get all the details. So, it kind of makes some sense, but it takes a little bit of time thinking about it. Okay, as I said, it does take some time, and the chapter 4 from Norman gives a good account of it, so it gives a quite detailed account. So if you kind of didn't follow my explanation, doing the reading and getting Norman's view of it might help. Yeah. Okay, but as I said, it's definitely the hardest experiment that I'm going to talk about in terms of the inference that the researchers are trying to draw, just because it involves a simultaneous comparison of three conditions. Nothing else I talk about is going to be as hard.
Okay.
Okay, thank you.
Hi.
Hello, sorry.
I have a quick question. So today is my second time of watching that video where a gorilla just walked past.
Yeah.
And I remember the first time I watched it, I counted 15 as well as the right number, and I didn't see the gorilla.
Yeah.
But today, I know that the gorilla is coming, so I was like shifting my attention to the gorilla, but I can still count correctly.
Yeah.
So does that mean it doesn't really require full capacity to?
Look, no, this is something that is entirely dependent on sort of expectation and anticipation. And so once you've seen it and you know it's going to happen, you're prepared for the gorilla. You can kind of detect the gorilla while. It's not that counting the passes is such a really difficult, demanding thing that if you happen to attend to the gorilla, you're going to completely lose it. The fact that you can, there's the gorilla while still keeping track of the passes, indicating that the passing task while it's loading your attentional system is not so demanding that if you look away for a moment that you're completely, you've completely had it. It simply says that by setting up the task in a particular way, by directing attention to the white team, that's sufficient for, if you don't know that anything else is going to happen, for you to segment the visual field in such a way that you just don't notice the gorilla. Okay. Yeah.
So it's not that much about the demandingness of the task, but the act of actually shifting.
It's the fact. If you think about it in kind of filtering terms, you basically say, well, the white people are the relevant task. The black people are distractors, because white people are the ones that I'm counting, and simply by virtue of the fact that you have allocated your attention to the white people, you just process everything else as black stuff. Black gorillas and black people are just treated in exactly the same way.
Okay, cool. Thanks.
Good.
Hi, sorry, I'll be quick. I'm just really, would you mind quickly re-explaining just this one here for the,
Yes.
It's just the one, it's just not quite comprehending. So it's for the early selection.
This is a really demanding experiment, and it's probably worthwhile reading the chapter, the Norman chapter, where he discusses it at length. Because if you don't follow my explanation, maybe you'll like Norman's better.
So I understand the one for.
Okay. So what you don't understand is why early doesn't predict and is less than or.
Yes.
And so look, the argument is that if you take a strict early selection view, filtering should occur because of the way you're sort of setting up by, or attenuation should occur by the way you monitor the environment. But the attenuation should be a property of filter, which occurs prior to the limited capacity system, whose job it is to distinguish between targets and non-targets.
Okay.
And so if that only happens, that distinction between targets and non-targets is only made in the limited capacity channel. It shouldn't affect filtering, and it shouldn't affect how you attenuate. So in other words, in other words,
both should be filtered through with the same degree of importance.
Yes, so basically 2 targets or 1 target and 1 non-target should be attenuated to the same degree.
Yes.
You wouldn't expect differential attenuation depending on whether it was a target or not.
Great.
That fine?
That's cleared it all up. Thank you so much.
And if you're still if you're still uncertain, read Moray as well. Because one of the nice things about Norman is that he actually includes excerpts. So there's one big section which is just from Moray's original study, which is kind of interesting just to get how people say 1970s were talking about this. Okay.
Right. Thanks so much.
I hope the weather's better out there than it was when I came in. Yeah. Okay, that's all I need, slowing down. Okay, all yours. Thank you. Sorry.